For this lesson, we're going to talk about solving optimization problems, and this is part of the applied optimization problems section in the book. So, in fact, that's the only part of that. Then after this is L'Hopital's rule, which is a lot of fun. Okay, so learning objectives to set up and solve optimization problems in several applied fields. So optimization problems are usually trying to find the maximum or the minimum value of a system. Here's an example. A rectangular garden is to be constructed using a rock wall as one side of the garden and wire fencing for the other three sides. And there's a picture down below. Given 100 feet of wire fencing, determine the dimensions that would create the garden of maximum area. So essentially what we have is the rock wall. I should probably go to draw instead of lasso. So we have this rock wall, and then there's going to be this fenced-in area for the garden. And we can call this side X, and this side X, and this side Y. And what we know with this 100 feet of wire fencing, we know that 2x plus y equals 100. And the other part of this is we want a maximum area. So area for a rectangle like this would be x times y. And the idea is to get this area function in terms of just one variable. So if we take the other equation we know and solve for y, y equals 100 minus 2x. So we can write area as x times 100 minus 2x. So area could be a function of x, would be, and I'm going to write this in descending order, negative 2x squared plus 100x. Now, in your pre-calculus days, you would have done the negative b over 2a thing to find the vertex, and that's what we're after, but we're going to practice using some calculus skills for this. So we'll take that first derivative. We end up with negative 2 times 2x plus 100, and we take that negative 4x plus 100 and we set it equal to 0, because we're trying to find the critical values. If we subtract 100 from both sides, we have negative 4x equals negative 100, and divided by negative 4, x equals 25. The y value, as we found earlier up here, was 100 minus 2x. So it'd be 100 minus 2 times 25, or 50 feet. So the dimensions are going to be 25 feet by 50 feet. Okay. Now we have another one like this. Here's a garden. Oops. Okay, moving on. Where's the other one? Here it is. So it's the same kind of problem. Determine the maximum area if we want to make the same rectangular garden as in figure 2, but we have 200 feet. So we still have this wall, and then we have the structure. I'm going to call again that x, and this is y. So that 2x plus y equals 200 this time. Area, we're still looking for it to be a maximum, and that's x times y. And so if we solve for y, y equals 200 minus 2x. So this is going to be x times 200 minus 2x. Or area in terms of just x is going to be negative 2x squared plus 200x. So again, we take the derivative of the area function. That's going to be negative 2 times the 2x plus 200. So we take that negative 4x plus 200, set it equal to 0. Negative 4x equals negative 200. Divided by negative 4, x equals 50. Y equals 200 minus 2 times 50. So that's 100. So it's 50 feet by 100 feet. Okay. Now, the book has this really nice set of steps you can follow to do problem solving strategies. Introduce all variables. If applicable, draw a figure and label all the variables. Determine which quantity is to be maximized or minimized, and for what range of values or other of the other variable, if this can be determined at this time. Write a formula for the quantity to be maximized or minimized in terms of the variables. This formula may involve more than one variable, as we've seen. Write any equations relating the independent variables in the formula from step 3. Use these equations to write the quantity to be maximized or minimized as a function of one variable. Identify the domain of consideration for the function in step 4 based on the physical problem to be solved. And then locate the minimum or maximum value of the function from step 4. This step typically involves looking for critical points and evaluating a function's endpoints. Okay, we've been taking the derivative and finding things. Okay, so now we're going to do another problem. An open top box is to be made from a sheet of 24-inch by 36-inch piece of cardboard. So I'm saying this is 24 inches, 36 inches. By removing a square from each corner of the box, so a square comes out of each corner. We're going to call that x by x. So that if we were to make ourselves a nice three-dimensional type of drawing for this, the smaller side would be that 24 minus, I have x up here and x down here, so minus 2x. And the other side is 36 minus, I have an x here and an x here, 2x. And this height here is x. So our volume is going to be length times width times height. So this is going to be 24 minus 2x times 36 minus 2x times x. So volume is just a function of x, and that's going to be, if we multiply this out, it'd be 4x cubed minus 120x squared plus 864x. So we're going to take our derivative. That's 12x squared minus 240x plus 864. And from here, I'm going to take that and set it equal to 0. So 12x squared minus 240x plus 864 equals 0. And I could divide a 12 out of every term. And I would have x squared minus 20x plus 72 equals 0. So this is a case, this one's not going to factor, so we use a quadratic formula. So x equals negative 20 plus or minus the square root of 20 squared. Make sure no one thinks it's a minus there. 20 squared minus 4 times 1 times 72, all divided by 2 times 1. What we come up with here is x is 20 plus or minus 4 root 7 all over 2. So it's 10 plus or minus 2 times the square root of 7. Now, x equals 10 plus the square root of 7 is approximately 15.29. And x equals 10 minus the square root of 7 is about 4.708. So which one is a reasonable x? And remember, x is the side of the little square in the corners. Well, if it was at 15.29, it's going to be over half the distance across, and these are going to be overlapping, so that's not possible. So it couldn't be this value. So this value is possible. So our volume is going to be our volume evaluated at 10 minus the square root of 7 is going to be 640 plus 448 times the square root of 7, which is approximately 1825 cubic inches. Okay. Let's go on to another one like this with boxes. Suppose the dimensions of the cardboard in the previous example are 20 by 30. So we have our 20 by 30 sheet here. We have corners cut out. So if we look at our box that we end up from this, I don't do a drawing tonight. Okay, so we'd have 20 minus 2x here, 30 minus 2x, and then x. So the volume in terms of x is going to be 20 minus 2x times 30 minus 2x times x, and that's going to be 4x cubed minus 100x squared plus, sorry, that's 100, plus 600x. So our derivative, v prime, is going to be 12x squared minus 200x plus 600. And I just did the same mistake. I didn't read all the instructions. And all it says is determine the domain of the consideration for x. So given that x can't be more than halfway across the shorter side, x would be in the interval from 0 to 10. If it's at 10, then you really have no width, you just have length. Okay, another problem. Talking about, this one's a minimization. So in this problem, an island is 2 miles due north of its closest point along the beach. So we have an island out here. This is 2 miles. And then a visitor staying at a cabin on the shore that is 6 miles west of that point. So let's say here's a cabin. The visitor is planning to go from the cabin to the island. Suppose the visitor runs at a rate of 8 miles per hour and swims at a rate of 3 miles per hour. How far should the visitor run before swimming to minimize the time it takes to reach the island? Okay, so this distance is 6 miles. And so the visitor would go down the shore along the beach so far and then turn and swim. So it'd be something like this. So this is how I like to do it, because I don't like to have too many complicated things inside my under a radical. So I'm going to call this x and call this part here 6 minus x. The book did something a little different than that, but this is how I prefer to do it. So if you think about that triangle, that is a right triangle. This is 2, this is x, and this is, call it h, I guess. H squared equals x squared plus 2 squared. So h would be the square root of x squared plus 4. And that's this distance here, the square root of x squared plus 4. Now, distance equals rate times time, and we want time. So time equals distance divided by rate. And so the time for this is going to be the different distances. So the 6 minus x, which is the distance the person runs on the shore, and divided by the rate of 8 miles per hour for running, plus the time for swimming is the square root of x squared plus 4, that's the distance swimming, divided by 3, because that was the speed for swimming. And that is our time function. So the derivative of t of x is going to be negative 1/8 plus, then we have this derivative of, that's an x squared plus 4 to the 1/2 power, so 1/2 times 2x is the derivative of what's inside, and down below is the square root of x squared plus 4, because that becomes a negative 1/2. I can't forget my 3, that would mess everything up. And from this, the 2's would divide out. So we would have negative 1/8 equals x over, no, let's just say plus right now. That's a little bit of a foreshadowing. Plus x over 3 times the square root of x squared plus 4. Let's set that equal to 0, or that's, sorry, just that's a cleanup. We're going to take this negative 1/8 plus x over 3 root x squared plus 4 and set it equal to 0. So this x over the square root of 3 times the square root of x squared plus 4 would equal 1/8. So I'm going to cross multiply. 8x equals 3 times the square root of x squared plus 4. Now we're going to go to solve this, and to solve this radical equation we have to square it. So we have 8x, we're going to square, equals 3 times the square root of x squared plus 4 squared. So 64x squared equals 3 times the quantity x squared plus 4. 64x squared equals 3x squared. Oh, that shouldn't be a 3, that should be a 9. 9x squared plus 36. So we can subtract 9x squared from both sides, and 55x squared equals 36. So x squared is 36 over 55. So x would be the square root of 36 over 55. We're only going to go with the positive. We don't have to worry about the negative or the principal square root. So x would be 6 over the square root of 55, which would be approximately, I didn't work that part out because of what I did next, is I said we're looking for 6 minus x, so that's 6 minus the square root of 36 over 55, which that is approximately 5.19 miles. So the point is, the person would run down the beach 5.19 miles. The running part, this is 5.19 miles. And then swim that length. Okay. Next, this is a similar problem. Suppose the island is 1 mile from shore. The idea behind this is a problem students would work out. 1 mile. I'll show you how to work it out. Still have the cabin here. This time it's 15 miles down the shore. So the person's going to go down so far and then swim. So this would be 15 minus x. Well, this is x here. And this would be the square root of x squared plus 1. This is the hypotenuse of a right triangle. So our time in terms of x for this one is going to be that 15 minus x divided by the rate for running is 6 miles per hour, plus we have the square root of x squared plus 1 over the rate of swimming is 2.5 miles per hour. So t prime of x is going to be negative 1/6 plus, and the same type of thing with the derivative. We get a 1/2 from that being the power coming out front. Then we have times 2.5 times the square root of x squared plus 1. And then we have the derivative of what's inside, which is a 2x squared plus 1, so times 2x. That could be cleaned up a little bit. The 2's divide out. So negative 1/6 plus x over 2.5 times the square root of x squared plus 1 equals 0. I set it equal to 0. So x over 2.5 times the square root of x squared plus 1 equals 1/6. We're going to cross multiply. So 6x equals 2.5 times the square root of x squared plus 1. At this point, I think it's worth dividing both sides by this 2.5, because that'll give us 2.4x equals the square root of x squared plus 1. And then we can square both sides. And that is 5.76x squared equals x squared plus 1. So we can subtract the x squared from both sides. Let's start going to the right now. We would have 4.76 x squared equals 1. X squared equals 1 divided by 4.76. And x would equal positive, square root of that. It's going to be 0.458 miles. So the person's going to run 15 minus 0.458. That's going to be 14.54 miles. Okay. Let's keep going. This one has a lot of examples in it. Okay, maximizing revenue. Owners of a car rental company have determined that if they charge customers P dollars per day to rent a car, or P is between 50 and 200, the number of cars they rent can be modeled by the linear function n of P equals 1000 minus 5P. Okay, and then they want to know how much to charge to rent the most cars, or to make the most money. Because we know if they do charge 50, they rent them all. Okay, so I'm going to show you the steps that they'd like us to do, but I won't do that for most of the problems. Step 1, P is the price, and R is revenue. Step 2, our goal here is to maximize R. Step 3, to find R, it's going to be the number of cars rented times the price per car rented. Step 4, to make R a function of P, we're going to multiply what N was. N is 1000 minus 5P, and then we're going to multiply that by P. So I want to make the point that this N is this 1000 minus 5P. So that means we have R of P is going to be equal to, if I put this in descending order, negative 5P squared plus 1000P. So our step 5, we're going to find the max revenue in the interval from 50 to 200. So step 6, we're going to find r prime of p, which is negative 10p plus 1,000. So we could take that negative 10p plus 1,000 and set it equal to 0. And then 1,000 equals negative 10p, or positive 10p at that point. Divided by 10, p equals 100. So at 100 cars, they'll sell the most, or make the most money. So revenue for 100 is going to be equal to negative 5 times 100 squared plus 1,000 times 100, and they'll get from that $50,000 a day. Okay, let's keep going. Another car rental problem. Okay, so in this case, our revenue in terms of P would be the price times 750 minus 5P. So that's going to be negative 5P squared plus 750P. And then we want to find the derivative. R prime of P is equal to negative 10P plus 750. So take the negative 10P plus 750, set it equal to 0, divide by negative 10. That should be P minus 75 equals 0. I'm laughing at myself because I'm thinking 2 steps ahead and I forgot a step here. So P equals 75. That's the price. I will maximize revenue. Okay. A rectangle is to be inscribed into an ellipse. This is a little more involved problem. I should say a lot more involved problem. So a rectangle is to be inscribed into an ellipse. So I'll draw the ellipse. It's x squared over 4 plus y squared equals 1. So this ellipse is going from 2 to negative 2 this way, and then 1 to negative 1 this way. Okay. And then we will have our rectangle inscribed in it. Okay, not perfect, but that's what it is. And just take this point here, we'll call that xy. And what we're looking at is we have length and we have width. So if we call this part length, this part width, length equals 2x and width equals 2y. So area is length times width. Let's do a dot width. So that's going to be 2x times 2y, or 4xy. But maybe I should pause there for a second before I do that. Yeah, before I do that, let me do this. We know that we have the equation x squared over 4 plus y squared equals 1. So x squared over 4 plus y squared equals 1. So y squared equals 1 minus x squared over 4. So y would equal the square root of 1 minus x squared over 4. Okay. And if you recall, we have the width here. Width equals 2y. So that's going to be 2 times the square root of 1 minus x squared over 4. So to make this not look so bad, what if we brought that 2 inside? By bringing this 2 inside, it becomes a 4, because square root of 4 is 2, or 2 squared is 4. So 4 times 1 minus x squared over 4, which is the square root of 4 minus x squared. Okay. This allows us to relate x to y, or y to x. Now we look at the area, which was L times W. We can have 2x times the square root of 4 minus x squared. So area as a function of x is 2x times the square root of 4 minus x squared. Sadly, it doesn't clean up any more than that, and we will have to take a derivative here. So I'm just going to slide this over. A prime of x, the derivative here, is going to be 2 times the square root of 4 minus x squared plus it's going to be 1 over 2 times the square root of 4 minus x squared. I got stuff inside to deal with, that'll come in the numerator. So the derivative of 4 minus x squared is negative 2. I had that 2x from earlier, so I will keep that 2x. So 2x times negative 2x. That's what it is. Derivative of x squared, negative x squared is negative 2x. Okay, so we're going to end up with 2 times the square root of 4 minus x squared minus 4x squared. Oh wait, that'll reduce, won't it? Minus 2x squared over the square root of 4 minus x squared. So if we take that and set it equal to 0, 2 times the square root of 4 minus x squared minus 2x squared over the square root of 4 minus x squared equals 0. So 2 times the square root of 4 minus x squared equals 2x squared over the square root of 4 minus x squared. We multiply both sides by the square root of 4 minus x squared. And we end up with a 4 minus x squared. I got a 2 out in front of this. Equals 2x squared. So 8 minus 2x squared equals 2x squared. So 8 equals 4x squared. So if I divide by 4, 2 equals x squared, and x equals the square root of 2. Now, let's go ahead and just find some good space to work. I'm at the end of my, there's my wall. Okay, so y was equal to the square root of 1 minus x squared over 4, so it's square root of 2 squared over 4. So that's going to be square root of 1 minus 1/2, because it's 2 over 4. So it's the square root of 1/2. So it's 1 over the square root of 2. So our area was 2L. No, it was 2x times 2y. So it's 2 times the square root of x times 2 times, well, let's use 2 times the square root of 2, I should say, times 2 times 1 over the square root of 2. So these would divide out, and we're left with 4. So 4 is the area of this figure. It's the area of this inscribed rectangle. Okay. Okay, I'm going to move on to the next one. Next one is very similar. it's one of the green ones. So it says modify the function a in the rectangle to be inscribed in the circle x squared plus y squared equals 1. So we'd have the circle not drawn perfectly, but let's make that's there. So we're looking at having an inscribed figure here. Okay, and any guesses as to what kind of figure that is? Okay, joking. So the domain here for x, the biggest it can be, is 0 to 1. 0 to 1. Obviously it won't be that big. So once again, area is 2x times 2y. So our area is going to be what? Well, let's do a little side math work over here. I think all they want us to do is, oh, what is the domain of consideration? That's all we had to do. It's just the domain. Here I am going drawing figures and all that. So 0 to 1 is what we're after. That's all we have to do. It has to be within that. Okay, I'm going to move on to the next one because this has already gotten long, so I'm not going to do problems you don't have to do. We are standing on top of a 768-foot building, so 768-foot building. And we launch a small object upward. The object's vertical position is given by h of t equals negative 16t squared plus 32t plus 768. What is the highest point it reaches? So we do the derivative h prime of t. It's going to be negative 32t plus 32. So we take negative 32t plus 32 and set it equal to 0. Negative 32t equals negative 32, where t equals 1. So h of 1 is going to be negative 16 times 1 squared plus 32 times 1 plus 768. And the answer is it gets up to 784 feet. Okay, a couple more problems. Doing great. Now we're going to minimize surface area. We have a rectangular box with a square base and an open top. So draw the box. Doesn't look very square, but call that X. Call that X. Call this Y. Okay. So the volume of this box is going to be x squared y. And it says that the volume is 216 cubic inches. So you can say y equals 216 over x squared. You're saying, why would you do that? Because they want to know the minimum surface area. So if we unfolded this box, we'd have this square in the middle, it's x by x. Then we have four sides that are x by y, x by y, x by y, and x by y. So the surface area is going to be x squared plus 4x times y. So I could take this expression and put it in place of the y. So surface area in terms of x is x squared plus 4x times 216 over x squared. So the x's would divide out. S of x is x squared plus 864 over x. So our derivative s prime of x is going to be 2x plus 864 times -1 times x to the -2. I just brought that up to help me see this. So it's going to be 2x minus 864 over x squared. So we can take that 2x, oh, wrong color, 2x minus 864 over x squared and set it equal to 0. So 2x equals 864 over x squared. So that 2x cubed, we multiply both sides by x squared, equals 864. X cubed equals 432. So x equals the cube root of 432. And that would be the cube root of 216 times 2, which is 6 times the cube root of 2. So that's our x, and that's approximately 7.5595. And our y would be equal to 216 over 6 times the cube root of 2, that much squared. And that's going to give us 6 over 2 to the 2/3, which equals 2 times 3 over 2 to the 2/3, which equals 3 times 2 to the 1/3, which equals 3 times the cube root of 2. So our surface area, 6, so we have to solve for x, times the cube root of 2 is going to be 864 over 6 times the cube root of 2 plus 6 times the cube root of 2 squared. And what do we have out of that? 108 times the cube root of 4 square inches. Okay, that was quite a bit. We have one last part. And here it is. Consider the same open top box, which is to have the volume of 216 cubic inches. Suppose the cost of the materials base is 0.2 20 cents per square inch, and that's for the base, and for the sides is 30 cents per square inch. And we're trying to minimize the cost of the box. All they're asking us to do is write the cost as a function of the side lengths of the base. So cost is going to be 0.2 times the x squared, because that's the base, plus 3 times 4xy. So it's going to be 0.2x squared plus 1.2 times 216 over x squared. So it's going to be 0.2 x squared plus 259.2 over x squared. There's our expression. Okay, quite a long lesson. They seem to be getting longer and longer. Okay, now the next section we'll get into, we have three subsections. So, my gosh, getting near the end of chapter 4 though. That's kind of cool. Okay, bye.